Okay, let's talk about higher degree models. Models is the word we use because it's a little bit fancier than word problems, but when we model, we want to make our equations stand for something. With higher degree, there's not that many great applications. There's a lot of things that a parabola, a second degree function will model. Straight line, there's a lot of those, exponential even. With higher degree, there's not so many. There's only a few good examples in our textbook, so I'm just going to give you one that doesn't have any context just so you can learn the skills, and then when we practice, it'll be more of a word problem. So you should have learned that 2 points determine a line, meaning if I say here are 2 points, what's the equation of the line? There's only one answer. Only one line goes through 2 points. 3 points determine a parabola. 4 points determine a cubic function. There's only one cubic function that goes through these 4 points. And if we want to find that, which is my first question, we're going to use the calculator if given those 4 points. So what we want to do is go to the stat menu and enter the x's into list 1 and the y's into list 2. So negative 1, 2, 3, and 4 versus negative 10, negative 7, 2, and 45. We've done this for parabolas before, so now we're just going to get a cubic. So now if you go back to stat, go over to calc, and you should have a cubic regression option, option 6 for me. If you have a little bit newer calculator, you have this menu that says L1, L2, and then you should have a line that says store reg EQ, and that's just saying where do you want me to put this equation? Put Y1 there. If you have a calculator that looks like mine, we're going to type a Y1 right now. Y1 is under vars, which is a few buttons above the 9. Go to the right to Y vars, hit enter on function, and hit enter on Y1. Now when you calculate the equation, it's not only going to tell you the equation, but it's going to go ahead and put it into Y1 so that we can look at its graph. So when I hit enter, here's my equation. A, B, C, and D are 3, negative 10, 2, and 5. That little r squared equals 1, that just tells us that it's a perfect fit, meaning these points are exactly on the line. If we had put a bunch of points in and said, give me the best possible cubic function, it wouldn't have been a perfect fit. It would just be as close as it could be. So my equation, 3, negative 10, 2, 5, f of x or y, 3x cubed minus 10x squared plus 2x plus 5. 3, negative 10, 2, 5 are the coefficients. All right, so that's the easy way to do cubic regression. Find the cubic equation that goes through those points. Now, with it stored, see what it did. See that 3, negative 10, 2, and 5? It stored them in my Y1. Now, sometimes your calculator does funny things. Like instead of saying 3x cubed, it says 3.000, a bunch of zeros, 96. Calculators find numbers in kind of funny ways. So sometimes if they mean to say 3, they'll say a number that's barely over 3. So we won't worry about that right now. So if you go to graph, you should see that your picture was already put in so we can look at its graph. So this is a positive cubic. It leaves bottom left, top right, the end behavior. And now we can use the calculator to find out things about our graph. The next question is, what is f of 1? In other words, when x is 1, what's y? So second calc, second in the trace button is the calc menu. If you have an equation or a graph and you want to find out information about it, this is where you want to go. Hit enter on value because we want a value of the function, and then just type in whatever x you want. So f of 1 is 6.56 times 10 to the negative 11th. Another funny calculator way of saying 0. Technically, this is 0.000 with 10 zeros and a 6. If that ever happens on your calculator, that means 0. It's a little complicated, and it doesn't look right, but again, that's the way calculators work sometimes. Okay, next, when does f of x equals 30? In other words, y is 30, what's x? Calculators work one way. You have to plug in what y equals, and then you can substitute in any x you want. So I cannot just tell my calculator, hey, y is 30, what's x? So how do we get around that problem? First of all, let's get our picture adjusted to where we can see 30. So I'm going to make y max go up to 40 and go back in my picture. So now I'll at least be able to see where the line or where the graph reaches a height of 30. Now it would be nice if I could say, calculator, y is 30, what's x? I cannot do that. So here's how we get around that problem. Go to y equals and graph the line y equals 30 and then go back to your graph. So what we're looking for is the x value where that happens. It looks like it's somewhere between probably 3 and 4. I'm not positive, but here's how we find that solution. Second, calc, intersect, option 5. First curve, second curve, I can basically just hit enter because I only have 2 curves on my screen. Guess, scroll your cursor over to the intersection just to let it get a head start where it looks, and we should get an intersection. So you can see at the bottom, 3.75 we'll call it, is when y equals 30. All right, so a little bit of maneuvering we have to do to plug in a y. Okay, relative max and relative min. What that means is, where are the peaks and valleys? If you ever hit zoom 6, it will take you back to your 10 by 10 grid. All right, so relative max, that's asking for the location of this little peak right there. So what are the x and y coordinates of that little peak? Again, second trace is where we find all this stuff out. Maximum 4, left bound and right bound. This is just saying, give me a number that you know is to the left and a number you know is to the right, and I'll find for you the peak that's in between those x values. 2 options. You can either scroll your cursor somewhere to the left of the peak and hit enter, scroll it somewhere to the right of the peak and hit enter, and then try to get it as close as you can to the peak and hit enter, and it'll find it that way. So at 0.105, our y value is 5.10. 0.105, 5.10. All right, that's our relative max. A relative max isn't the biggest the function ever gets, because this function never stops growing. It goes all the way up to infinity. But this is on a little window, it's a peak. All right, it drops off to both sides. So that minimum that I can see on my screen, another option to finding those, the left bound, just type in a number that you know is somewhere to the left. It looks to me like it's somewhere close to x equals 2. So I'm going to do left bound 1, right bound 3, guess 2, and see it's somewhere close. So at 2.11 or 2.12, negative 7.12. 2.12, negative 7.12. 2.12, negative 7.12. All right, so that's just something you have to learn to do on your calculator. You'll do this in calculus using something called a derivative, but for now we're just going to use our calculators. So this is basically all calculator exercise. Okay, another type of example, quickly. This is a problem you will solve this year. You'll solve it in pre-calc. You'll solve it in Calc 1 with your strategies adjusting each time. So here's how we'll solve it as of this year. You want to make a box by cutting squares of size x out of the corners of a piece of cardboard and then folding up what's left. All right, so if we, let's see, we're going to get a box that looks like this. It won't have a top on it, but if you cut those squares out and then take this, what's left over, and fold it up, and then you would kind of tape the corners together or something, you would be creating a box. So the question is, what's the best we can do for volume? Do I want to cut out a big X? Do I want to cut out a little x? You could make a variety. We could make a box that looks like this if we just cut out a little bit. So the question is, what rectangle is going to make the volume of this box the biggest? If this is 20 and this is 10, what is this? All right. If I cut those rectangles size x out, wouldn't that length be 20 minus 2x? This would be 10 minus 2x. Do you agree with that? Okay. So now we're just going to throw those little squares, x by x squares away, fold up the sides, and create our box. So think about the dimensions of the box you make. This side, any 3D rectangular solid has 3 dimensions, and your volume is length times width times height. One of our dimensions is 10 minus 2x. The other one is 20 minus 2x. That's these. And the third dimension is x, because however big that rectangle is, when I fold those sides up and they meet, that makes the height of the box. So it might be like that. It might be, they're the same no matter what. X is what's varying. All right, you could cut out a tiny one, think about what's the biggest you could cut out. You can't cut out any more than 5. Would you agree with that? Because at that point, you've used up the entire width of your rectangle. So somewhere between 0 and 5 is going to make the biggest possible box. All right, so let's make an equation. Let me call this one V of x to stand for volume based on different sized squares that we cut out. The volume of this box is x times 10 minus 2x times 20 minus 2x. Length times width times height, right? If you wanted to multiply all that out and get something x cubed plus something x squared, you could, but if we're going to be using our calculator anyway, let's just type it in like that. I'm going to go back to y1, clear out the equations I was using, and type in my new one, my volume of this box. 10 minus 2x, 20 minus 2x, and x, length, width, and height. And then I'm going to set my window. Let's see what the graph looks like. See if we need to change our window. All right, it looks like we definitely need to change our window. All right, because I went from 0, 0 to 1, 144 really quickly. So I need, like 200 type numbers in my volume, in my y. X just needs to go from 0 to 5. I'm actually going to go -1 to 5, or to 6, to leave a little room on the edges. We'll go -200 to 200 just to see what it looks like. All right, so we could see these characteristics of cubic graph. We've just got a little bit of it. It's going to curve back upwards once we get past 5, 6, 7 somewhere. But if we actually zoomed out a little bit and made x bigger, we can see that this is a cubic graph. But the part of our graph that makes sense, the domain would be from 0 to 5. Because if x is how much you're going to cut out of each corner, you can't cut out anything lower than 0 or anything more than 5. So back to the original question, what is the max volume we can make? And while we're at it, what x should we cut out to make that max volume? So this is a graph of the volume. We want to find the maximum. It's somewhere between, I don't know, it looks like about 2. I'm just going to be safe and say 0 to 5, and I think it's somewhere near 2. So that gives me my max. At 2.11, I can get 192.45. 192.45. This is a classic example. Like I said, you'll do this in pre-calc, you'll do it in calculus again, but it's a good one because it gives us a nice cubic function in terms of x. All right, so there's 2 examples of higher degree word problems, one where you create the equation given the points, one where you kind of use geometry to create the equation, both cubics, both equally awesome. Young out.